Hey guys, welcome back. This video is going to be talking about how to check the conditions, calculate something called a test statistic, and how to calculate the p-value for a significance test for one population proportion. So our conditions are of no surprise to you, hopefully by this point. We're going to check our random, our 10%, and our large counts condition since this is a population proportion. However, it should be noted that our large counts are going to be dealing with the null parameter. So we're not going to use the p hat. We actually are going to use the null proportion. And the reason is because we assume that that is true from the beginning. So that's the number we have to work with. Remember, we haven't proven that the alternative is true. We haven't proven the sample hasn't given us enough evidence yet until we run the numbers. And we have to base that off of the null. So we always use P or P sub O if you want to look at that. But it's still going to be the same large counts as at least 10. We don't want to sample more than 10% of our population, and our sample should be random. So let's go back to this free throw shot. Going back to our free throw, when we're calculating our p-value, remember informally we calculated 3 out of 400, and we got a pretty small p-value. We can actually model this with a normal distribution. Notice they look very similar to a normal distribution when you get enough dots in your dot plot to simulate that. So we're going to go back to our sampling distribution parameters to be able to calculate that normal curve and figure out the standard deviation. So to do that, we need to construct a sampling distribution around what we consider to be the true proportion. So remember, we assume the null is true. So there's your 80% right there from that free throw shot. And then we get a sample at 64%. We say, hey, that's a pretty small likelihood of that happening. I think that's false. And we can calculate that using this formula. And remember the sampling distribution formula, P, 1 minus P over N, all under the square root? Well, that's the same standard deviation formula we use here. And we use P, we use the population because we assume the null is true. Our mean, just like any sampling distribution, is going to be the population proportion, which we are told is 80%. So we have to roll with that. So what does that look like? What does that look like? Well, we calculate something called a standardized test statistic. It's a z-score, folks. And that z-score is basically we're going to take our test statistic. So we're going to take our sample proportion. We're going to subtract our null proportion, so our parameter, 80%. We're going to calculate that standard error based off of the null. So we'll use the p. So here's the formula. Now, this formula that says standardized test statistic equals statistic minus parameter over the standard error. This is in your formula sheet. This ain't. So you have to be able to pick apart the things that go in there. So let's calculate this. Remember, we're always going to use the null because we assume the null is true. So our mean is going to be 80%, 0.8, and our standard error is going to be 0.0566. Put that in your calculator and double check that I'm correct. Hey, look, I did it for you. So we have 80%, 1 minus 80% over 50. Remember, we're doing 50 shots, and that is your standard error, 0.056. And so that's going to be what we use for our calculation. Well, how do we know it's a normal distribution? Well, remember our large counts. We're going to go back here and check this. So back on this previous slide, I had calculated 50 times 0.8 to be 40 and 50 times 0.2 to be 10. Both of those are 10 or more. So I can actually use a normal distribution here and be safe to have that my calculation be correct. So that's why I'm able to use the normal distribution because of those large counts. All right, so let's build this here. So we have our standard error, we have our mean. We know it's going to be a normal distribution. On your formula sheet, you have your generic test statistic. We use p hat minus p over the square root of p, 1 minus p over n. We're going to plug our numbers in, and we're going to get a z-score. We're going to get a test statistic, and that's our z-score in this case because this is a normal distribution. We haven't learned any other ones yet. If you carefully calculate that you can determine that the z-score is negative 2.82. Let me show that a little bit larger. And that's going to be your test statistic. That's going to be your z-score. And what we do with that z-score is we calculate a p-value from there. So once we have our z-score, we can figure out what's the likelihood of getting a value as extreme or more extreme in that direction. So remember that oh gosh, um, remember our p-value is the probability of getting a sample as extreme as that, assuming the null is true. So if I'm calculating the probability of getting a value as extreme of that, I'm going to go into my normal CDF. And since my z-score was a negative 2.8284, I'm going to calculate a normal distribution. Leave my 0 and 1 as my mean and standard deviation because this is a z distribution of getting a probability less than that z-score. And it's 0.002. It's really small. So always use that normal CDF. It's going to be a very small probability. And what does that tell us? Well, let's compare it to our original p-value. From the simulation, we got a p-value of 3 out of 400. Remember, that was about 0.0075. This p-value is pretty small, right? It's actually a little bit smaller based off the normal curve. It's 0.0023. In any case, how do they compare? Well, it's a little bit smaller, but is the conclusion going to be the same? Absolutely. They're both very small, so we're going to reject the null hypothesis. In other words, this person's lying, guys. They don't shoot 80%. So remember, the standardized test statistic is a z-score for now. There's going to be other ones that we're going to calculate eventually down the road, but for right now, it's just a z-score. It's our sample proportion minus our null proportion over the standard error using the null proportion. Let's do an example. So on this problem here, according to the US Census Bureau, the proportion of high school students who have a part-time job is 25%. An administrator at a large high school suspects that the proportion of students at the school who have a part-time job is less than the national figure, would like to carry out a test at the 5% significance level. Here's the hypotheses. So we have P is equal to 0.25 and P is less than 0.25 for the alternative. And the reason it's less than is because administrator suspects that the proportion is less than the national figure. So that's based off the wording in the problem. P is the population proportion of students at the school who have a part-time job. The administrator selects a random sample of 200 students from the school and finds that 43 of them have a part-time job. We got four things to ask for here. Explain why the sample result gives some evidence for the alternative. Check if the conditions are met. Calculate the standardized test statistic and interpret the p-value. So let's go through all the steps. Why does the sample result give some evidence for the alternative? Well, let's look at what we're calculating here. It's 43 out of 200. 43 out of 200. When you divide those out, you get 0.215. Now look at the alternative. Proportion is less than 0.25. Well, that is less than 2.5, so there's your evidence. Now, check the conditions. When we're checking our conditions, we want to make sure that our random sample is met. And right here, the word random does pop up. So our random condition is met. We're going to assume that 200 is less than 10% of students at a large high school. We don't really know the number of students at the school, but we have to be able to make some assumptions in this case to run the test. The last thing is we're going to check our large counts. Remember, which number do we use for our proportion? That's right, we use the 25%. We use the null because we assume that the null is true. So we always do our number in the sample, which is 200, times the null proportion, so 0.25, that's 50. And then n1 minus p is going to be 200 times 0.75, which is 150. Both of those are more than 10, so it satisfies the normal slash large counts condition. Let's calculate our test statistic. This is going to be the one that requires the most amount of calculations. So because we have to be able to use our statistic, which is our sample proportion, we have to calculate our standard error, which is p1 minus p over n under the square root. We have to put that all into our z-score formula. So very carefully, it's going to look like this: 0.215 minus 0.25 over the square root of 0.25 times 1 minus 0.25, which is 0.75 over 200. So calculate that, see what you get. I'm going to use the fraction menu here. If you have a TI-84, you can do alpha y equals. You can pull up a fraction, so 0.215 minus 0.25. And then on the denominator, you can do second square root alpha y equals. And we can do our everything under the square root inside there. So 0.25 parentheses 0.75. You could do 1 minus 0.25. And then on the denominator, it'll be 200. And that'll get you a z-score, a test statistic of negative 1.143. So let's calculate our p-value. To calculate our p-value, we want to use a normal distribution, but it's based off of the number, right? So if the z-score is negative 1.143, we're looking to go the probability of being less than that. So we use our normal CDF, and our lower bound is going to be negative infinity. Our upper will be a negative z-score, negative 1.143. Keep 0 and 1 as your mean and standard deviation. And you're going to get about 12.65%. Not very small, but that's going to be our p-value. So let's interpret the p-value. So remember, the p-value interpretation is, here's your blanket statement. Assuming the null is true, there is a, whatever the p-value is, probability of getting a sample as extreme by random chance in a random sample of whatever your sample size was. In context, assuming the true proportion of high school students with a part-time job is 25%, there is a 12.65% probability of getting a sample of proportion of 0.215 or less. Why less? Because of here. By chance alone, in a random sample, what are we sampling? 200 students at this school. That's your interpretation. All right, we'll stop this video. The next video will cover the one versus two-sided tests and more calculations with that. Thanks for watching this one.